Let us begin. Now, for the talk of Vasily Olegovich Manturov, Parity, Cobordisms, Rules, Virtual and Classical Rings.
Thank you.
Virtual now became classical.
So thank you very much, and it's a great pleasure of mine to have the possibility to give the second talk here. Today I'm going to argue that if some topological knot theory, or maybe not only knot theory, I'll talk about that later, some diagram is complicated enough, then it reproduces itself. My talk will be more functorial, somewhat more functorial and more, I would say, have more applications than the talk I gave last week. And the idea is as follows. So if we have an object like that, and if it's complicated enough, so we can decrease it in one term and we try to increase. So here I perform the Reidemeister move, the second Reidemeister move. So then we can get the initial object by smoothing, by getting some decrease in operation. And I'm going to argue how to get to that, and I'm going to somewhat understand more and more reasons when it happens. First of all, the main hero, the main protagonist of my talk is the parity, and the Gaussian parity is the usual thing one associates with a knot. So if we have a knot, then we have its Gauss diagram, which is constructed in the usual way, and then we'll look at its chords, and we see how many chords are linked, or how many chords intersect with that one, and we see whether chords are even or odd. So this is an example of a virtual triple knot. You see that here I disregard virtual crossings. So if I have a virtual knot diagram, I just consider them as artifacts of the planar drawing. So this is the virtual triple, and this is its Gauss diagram. So this Gauss diagram is somewhat decorated. I mean, so I here put pluses because of the local right numbers at 1 and 2, and also I put some arrows which respect the over-under information and crossings. But in fact, I will not dwell very much into the information of over-under, at least 2 additional bits of information. And actually, I will mostly concentrate on the parity, which is odd and which is even, and in the above picture, both crossings are odd. Both classical crossings are odd, virtual crossing doesn't count at all. So the main theorem, which I'm going to prove completely and which I stated last week, that for any knot theory, if we have a diagram with crossings which are odd and which is irreducible in the sense that there are no bigones, there is no possibility to decrease it in one term, then it's minimal in very strong sense. So that's the formulation of the theorem, so that every equivalent diagram has the initial diagram inside that. Better to say that not just K prime contains K, but the frame of K prime, when we forget about over-under and other bits of information. So actually, this minimality yields non-triviality and non-classicality, because in the classical case, so everything is even. So we have some very easy proofs that many things are minimal, and actually minimal in a very strong sense, so that we can find the initial diagram inside. So and actually, I'm now going to tell about the main two, and I'm somewhat repeating what was the last week. So to have the invariant which proves that theorem, I will need smoothings. They are just similar to those smoothings coming from the Kalkin bracket, like that. Then I construct the bracket. So this is the formula for my parity bracket. So we have a 4-valent diagram here, and then I take all possible smoothings at crossings. I smooth only at even crossings. I don't do anything to odd crossings. So odd crossings remain rigid crossings, And I take all those diagrams which I obtain after smoothing, so I call them KS when S is the state. And the resulting object will be valued in Z2 linear combinations of graphs modulo second Reidemeister moves only. Second Reidemeister moves only. And the main theorem, which proves the initial theorem about minimality in a strong sense and the fact that K prime contains K, is the fact that for an irreducibly odd graph K, we have that the bracket K here is equal to K. So you see here K is considered in two different senses. In the left-hand side, K is subject to moves. So this is a sort of knot, a sort of curve, a sort of equivalence class. And in the right-hand side, it's something modulo only second Reidemeister moves. So actually, second Reidemeister move is almost nothing. We can take the minimal diagram and we get its representative. It has a unique representative. So here, this such equality means that the diagram evaluates to itself, and such equality is a source of theorems like which lead to a partial classification. So here I drew possibly the simplest irreducibly odd diagram. So I take this Gauss diagram, and I know that it's minimal, and I know that it's non-classical, and I know that every diagram which is equivalent to that reproduces itself. So if I draw another diagram with six crossings, or a chord diagram with 6 chords, it will not be equivalent to that because it cannot contain it. Well, see, unless they are just equal. So this is a partial classification. For those irreducible odd diagrams, I have a classification. Right? Now I'm going forward, and actually, what do we have here? So I want to emphasize something, and in the very beginning we had the set of all Reidemeister moves. So we had a sort of dynamical object. So we had a knot. We had an equivalence class. So relations were by no means reductive. So in order to classify knots, we should increase and decrease and do many things. But here, in the right-hand side, we had only Reidemeister 2 move. And it's reductive. So actually we have graphs and Reidemeister 2 moves and nothing more. Then we can decrease and decrease and decrease, and finally we end up with the minimal representative, which is unique. So of course we lose some information. We pass from the equivalence class to its invariant. It's not the complete invariant. But what we gain is the reductivity, and reductivity is one of the main properties that we gain by using parity. So one of the main things we get by using parity is a reductivity. And now let's prove the main theorem. Let's do what we sketched the last week. And actually, here before proving that, I mentioned that this works for any other parity. And actually, many theorems here will hold whatever parity we take. So now I'm going to both to give a proof and to analyze what ingredients I need to get this proof. And then I see that these ingredients, so-called parity axiomatics, holds in many other situations. And in every other situation, I will see that irreducible odd diagrams will mean some other set of diagrams. And for other knot theories, in other circumstances, I will have the same theory, which will lead to another set of graphs. And now these are axioms for the parity. So for the first Reidemeister move, what I needed is the crossing should be even. For the second, it should be both crossings should be of the same parity. And for the third, the crossings, the corresponding crossings should be of the same parity, and the sum of all three should be even. This means that if I have A, B, and C here, and if I have A prime, B prime, and C prime here, then A should be of the same parity as A prime, B of the same as B prime, C of the same as C prime, and the sum should be even. This means that they are either all even, or there are two odd ones and one even one. And this actually happens for Gauss diagram. It's an exercise to see that for Gauss diagrams this holds. And actually, but this is not the only parity. This is what we need. And now the proof goes straightforwardly. So we see that all moves reduce to the second Reidemeister move. Here we gain this red activity. So you see, if we have the first Reidemeister move, this crossing is even, we have to smooth it. We can have this smoothing and we can have this smoothing. But this guy is forbidden because we have two components, at least two components. So the only smoothing is that, and this is equivalent to the initial diagram. For the second Reidemeister move, well, we can have four smoothings, but as in the case of the Kaufman bracket, this guy goes to 0 because it has two components. These guys are cancelled because we are over Z2. They are equal. And this guy gives us exactly what we need. Right? And for the third Reidemeister move, so this is the case when all three guys are even. So we just check that we have something, some count mod Z2 and 8 degrees, just as in the case of the Kaufman bracket. And for the third Reidemeister move, when we have two odd crossings, so these two upper guys are odd, what we get is that these two diagrams agree, and these two diagrams differ by a combination of two second Reidemeister moves. So you see, as in the trick of the Kaufman bracket, I reduce the third Reidemeister move to the second Reidemeister move. And what I use here is exactly the collection of those three parity axioms. So I can say, whatever parity we take, and by parity I mean something which satisfies three axioms. So this theorem holds, and thus the initial theorem holds. So, and actually, whatever parity we take, we can prove many theorems. We can prove minimality theorems in a strong sense. Well, if a diagram is irreducible and odd, and we have it inside any other diagram which is equivalent to the initial one, well, this effect of sitting inside means that many characteristics like genus, crossing number, and whatever else are less than or equal to. So we can prove not just facts, not just some estimates, but we know that some geometrical construction sits inside. And we can construct functorial mappings and coverings by deleting odd crossings. What do I mean? This was actually first mentioned by Turayev. The fact is as follows. So if we have a Gauss diagram, we can look at crossings of that, even crossings and odd crossings. And we can remove odd crossings. Remove odd crossings and consider this as a diagram of a new object. It can be a virtual knot. If we have some extra bits of information on it, it can be a free knot. And this map is functorial in the sense that if we apply Reidemeister move to that, then we get this, some Reidemeister moves, or maybe identical moves here, and this actually means that we get some functoriality. This is a functorial mapping. For example, if we have some knot, then we can cover it. Or we can just delete odd crossings. So one thing is that we just delete odd crossings by marking them as virtual. This means nothing at the level of Gauss diagram, we just delete. And the other thing is that we take two components and treat crossings which were formerly odd as crossings between two different components. So the example is given here. So here I have only one even crossing and two odd crossings. And now I construct two components, and even crossings will belong to one component, and odd crossings will belong to intersections of two components. This is the covering. And actually, virtual knots behave somehow as classical links, in the sense that we have different types of crossings. For links we have mixed and pure crossings. And now we get mixed and pure because of the parity. And explicitly it's given here. On the covering they are indeed mixed and pure. So, and actually these are some other things we can do, whatever parity we take. And
Yes. Clarify what you mean by covering. Does it literally mean when you're covering the underlying surface that it sits on?
Well, actually, finally, this will lead to the covering of the surface, but I can do without surfaces. I can do for free links.
But
so,
if I take it and I put it on the surface, there's a covering of the surface.
Sure,
that
sure.
describes it. So it really is a covering.
Sure, there should be a twofold covering like that. So there should be a two covering like that. And note that my protagonist is the free knot. And free knot, unlike virtual knot, doesn't have any surface to live in. And whenever a free knot wants to get operated by a certain Reidemeister move, it chooses a specific surface, and then it forgets about this surface. So this covering is defined without any surfaces, but we can do with surfaces. And also note that these objects, this functorial mapping is not idempotent. So crossings which were even can become odd here. So we apply F here, and we apply F for the second time, and this is not idempotent. We can iterate it, and everything becomes more or less functorial. There are lots of functorial properties, and here is some list of what we can do. And now the question is, where do parities come from? Actually, I said many things happen for whatever parity we take. Where do they come from? And there are some sources. Actually, there is a component-wise parity. So if we have two-component link, then we can say mixed crossings are odd and pure crossings are even. That's okay. Just check and see. And also, there is a homology parity. So if we have some knot theory in a two-surface, we can take some cohomology class of this Z2 cohomology class of that two-surface, with the only restriction that this homology class evaluates with 0 on the whole knot. Then we can take halves of this knot. By halves, I mean the following. So if we have a knot, then we can take some part of it going from a crossing to itself, and then I just evaluate this homology class of this part. It can be 1 or 0, and this is a well-defined parity. So if the Z2 homology class evaluated on this whole knot is okay, is 0. And also, actually, there is we can also define parities not only for all crossings, but if we have multi-component links, we can use one component as a supplement. We can use one component as a supplement and concentrate our attention to the other component. And then it will mean that for the other component we distinguish between even and odd ones, and these even and odd ones will give us a certain amount of information, though we don't distinguish between even and odd crossings of the first component. So schematically it's drawn like that. Some words first of all. So if we, why is that important? So we, sometimes it happens that we do some, why is that important to concentrate parity on crossing, or to, get some parity coming from a pattern, not just from a bare count of some Z2 elements. Because, for example, there are some transformations which do not change any of algebraic knot invariants, some mutations or some other tricks, or maybe connected sums of chord diagrams in different order, which do not change any homology and any other similar things. But now, if we try to do some patterns, so like this may go as follows. You see here, P is a pattern. So P is a component of a knot, right? And so here is the knot itself, and I want to classify crossings of K, whether K they are odd or even. I can say, well, let's take some cohomology class and evaluate on halves of K. And this cohomology class, well, I can say, let's take the torus and its meridian plus longitude or whatever. But it doesn't give so much information. But I can say, well, let's take the homology class which is given by that pattern. And then I can see that inside a knot this gives me something. But if I just make some move like that, for example, some mutation of the pattern which changes it, then in the right picture, all crossings will become even, because I define my parity with respect to the pattern P. and here I have P prime, I don't have P at all. And so, and here some crossings can be odd. So if I do some invariance in whatever way, brackets and so on, they will drastically differ on these two diagrams, though the move here is obtained by just some mutations. And also connected sums, you take A, B, and C, and you take A, C, and B. These are different connected sums. They give different patterns, they will give different invariants. Not invertibility, you invert the knot and the pattern will become different. And so on. So we have lots of parities coming from everywhere, and many theorems hold for whatever parity we take. And actually, so this means that parities themselves can be a sort of graph-like or not like objects. So at crossings we put either 1 or 0 depending on something. But this something itself can be a picture. So we can put an information depending on a picture, and this will give us invariance which is very seriously depend on the information. So we can get lots of information from that. And actually, one more property. So I already mentioned the reductivity, and now I want to mention locality. What does it mean, locality? So, well, assume I want to calculate some state, some invariant or whatever. I take a certain sum and I say here I put something, here I put something, modulo some relations corresponding to Reidemeister moves or any other similar moves. But now I want to say, look, this crossing is odd, and this crossing is responsible for the non-triviality of the knot. This crossing is locally non-trivial. And when I want to compute some further invariant, I can say, well, at this crossings we do that way, and then this crossing I do that way. I can consider different invariants. I can do different moves. I can treat them very differently, and I can localize the information about the non-triviality of the object at crossings. And this will be important. And now, as for knots and links, I have already mentioned that one can treat odd crossings of knots as mixed crossings of two components. And actually, there is something I have already drawn, so that if we have a knot K, then we can take f of K, which is obtained by deleting just all odd crossings, making them virtual, or by covering and getting a link. So that's it. And now, the problem where I cannot say whatever parity would take. And the problem where I'm going to higher dimensions, and when I'm constructing some parity for 2 dimensions. And this problem was actually, this study was inspired by Kant when he formulated a problem which was first solved by Scott Carter, I guess. And the problem was as follows: given a 2 surface, and given a curve on that 2 surface, is it possible to span our surface by a 3 manifold with a boundary, of course, and with a disk which is immersed or just different C1 mapped, possibly with cusps, to that 3 manifold, so that its boundary sits on our curves. So is our 2 curve null cobordant or not? And in general, if we have curves, can we construct invariants of null cobordant? So there are lots of abstractions coming from homological information, some pairings and many other things, and it was solved by various authors, and it's related to various subjects, but I wanted to construct it for free links, for free knots and links. When I understood that free knots are indeed non-trivial, why not to try to prove that there are non-slices of them? And why not to prove that there are Cobordism invariants for free knots? And now I give one Cobordism invariant of free knots, and the key ingredient here is that there is a way to define a parity for 2 disks or 2 spheres with generic intersections. So now let me state the problem which is more general than this one. And this problem is as follows. We have a graph, we have a frame covalent graph can be spanned by a two disk with singularity so that locally everything is three-dimensional.
Can you say it against the...
So that locally everything is three-dimensional. Locally.
What is the problem to say it against
So is it possible to find a two complex so that this complex is an image of a disk and all singularities are locally three-dimensional? So locally we can do everything for it as inside a three-manifold. So locally what can we have? We can have a triple point or we can have a cusp, or we can have a double line, but locally everything can be three-dimensional, but I don't care about the existence of a global three-manifold. Of course, I mean just that locally everything is three-dimensional. This complex is the image of a smooth disk, whose boundary sits on my curve. Of course, an abstraction to that problem is more difficult than the abstraction to the initial problem, and I will construct a very simple invariant which goes as follows. So here is a group.
So you're getting a sort of combinatorial version of what it would be to be a disk of three.
Yes. Yes.
But you're forgetting the three-manifold.
Yes, I'm forgetting the three-manifold. I'm trying to do everything completely combinatorial. So here is a group. Here is a group, and actually this is the infinite dihedral group. So this is the Kelly graph. So this is the Kelly graph. And I can write an element of that group starting from a Gauss diagram of a free knot. I just write down letters A and B depending on parity, and I will get an invariant. I will get an element of that group. And actually, it will turn out that this element of the group will be an abstraction to that problem I stated. And so first of all, the contiguity class of that element, the contiguity class of that element is an invariant of free knots just because of Reidemeister moves, but not only because we can also do Cobordism, and the key ingredient in the proof is that for two surfaces with intersections we can define correctly the parity for double lines. So we know which double lines are even and which double lines are odd, and this agrees with the definition of the Gaussian parity downstairs. Only Gaussian, unfortunately. I don't know how to do that for any parity we take for a higher dimension. Nevertheless, we can get an example. So this is the description of the Kelly graph I do here. Nevertheless, so this is the theorem that this is an abstraction. Here is a knot where this invariant is non-zero. Actually, here it's 16, and it can be equal to 8, and it's divisible by 8. And in fact, there is a lot of functoriality. So this Gaussian parity for double lines of two surfaces perfectly agrees with the mapping F with the covering. And actually, we can take a knot, we can construct the covering, we can evaluate the invariant of the covering. So we have a collection of numbers, but they will be only integer numbers, and they will not be pictures which persist. But nevertheless, it gives results of the following sort. For example, if we take a connected sum, when we break at different points, this can lead me to different results. So, for example, I can take the sum of A and B, where A and B are some virtual or free knots, and I can take the sum of A and B star, where B star is the same B but broken at a different point. And this invariant will be different. And this invariant will be different. So one of them can be sliced. For example, I can take A and A bar, where bar is just the reflection, and A plus A bar is always sliced. This is the initial, and A plus A bar prime will not be sliced because of that invariant. So this can be called by that invariant. And actually, two more things I want to tell. I promised to tell some words about groups. And for groups, I can say that instead of parity valued in just C2, we can localize much more information at crossings. And in fact, we can do the following. We can say, okay, what do we require for, say, the third Rademacher move? We require that A plus B plus C is 0 in Z2. But why don't we say the following? A is a generator of some group, B is a generator, C is a generator, and A times B times C is a relator. And then we will have a non-commutative group, and then we can have non-commutative parity. Of course, I don't have enough time to tell about everything, but there is non-commutative parity. And of course, if we take parity, take non-commutative parity and put it at crossings, we get more information, and we can enhance invariance in various ways. And actually, as for classical links, well, there is a standard construction actually. What do topologists do to get invariance of classical links? So, well, the complement to a knot has trivial homology, but to extract some more has homology equivalent to Z. But to extract more information, we should do something, do some covering and extract more information. And usually topologists convert this information into groups, variables, or whatever. But what we did with Michael Chrisman and then with Vladimir Krasnov is that we take a two-component link with one component fibered, and so that the complement to the fibered knot is can be covered by Sj times I. And Sj times I is the domain where virtual knots live. And if we have virtual knots, we can apply parity and whatever. And thus we can use all that machinery for classical links only. And actually there are lots of other ways how to study knots in three manifolds and many other things by using some topological construction first and pictures later, and we get all that factoriality and so forth. So my time is up now.
Please, questions?
Что у вас за сюрприз будет? Сейчас?
Сережа, и тебе не сказали, что за сюрприз? Председатель оргкомитета.
Сказали.
Сказали?
Он просто умеет держаться.
Ну он сейчас так как бы изображает, что не знает. Спасибо.
Только погромче. Ну, разбегайся все, начинайте.